the two broad topics. First, no-go theorems for discrete Wigner functions, and then alternative quantum representations of quantum computation. So this was my original planned outline. I'm going to start with some background information, some definitions to make sure we're all on the same page, and then go on to part 2 with these no-go theorems. But I really want to make sure I get through everything in part 3, these alternative quasi-probability representations. So instead of doing this, I'm just going to flash the main results in part 2 and go to part 3, and then if it's time again, come back and go through part 2 of the result. So first, definitions. The computational model we're talking about is quantum computation of magic states. So this is the computational model where you discrete field-out operations to the stabilized operations. The Clifford-covariant Wigner measurements, which by themselves can simulate efficiently on the classical computer. But when you allow non-stabilizer input states, these magic input states, you can restore universality. So this is the standard example of that down here, using this circuit, which has only Clifford gates and Pauli measurements. If you allow this non-stabilizer input state, you can effectively implement a T gate. And since Clifford plus T is universal for quantum computation, this shows that this model is universal. And the question we're going to try to answer is, which states can you feed into the input here while still doing useful quantum computations? So, because for example, if you just use stabilizer states, obviously there's nothing useful there because you can simulate everything on a classical computer. So we want to characterize which states are useful. So first, we're going to be talking about quantum computation on qudits that aren't necessarily qubits, the higher dimensional qudits. In that case, the Pauli measurements and Clifford gates look a little bit different. So first, these are the local generalized Pauli operators. There's standard clock and shift operators. And the Pauli group is the group generated by these two acting on n qudits. And you can identify these with ZD to the n cross ZD to the n like this, where the nth element is just telling you how many z's to apply on the kth. The kth element is telling you how many z's to apply on the kth qubit, and the kth element of AX is telling you how many X operators to apply. And then as usual, the Clifford gates are the normalizer, the Pauli group, and the unitary group up to overall phases. And then the stabilizer states are defined in the standard way as these +1 eigenstates. So the way we usually approach this question in the odd-dimensional case is by looking at, or one common way of approaching this in the odd-dimensional case is looking at the odd-dimensional discrete Wigner function. So I'll just spend a few slides going through this definition. So when you're talking about odd-dimensional qudits, so that's when this D here is odd. The phase space over which the Wigner function is defined is based on these non-contextual value assignments on E, where E is the set of labels for the Pauli operators. So these are functions from the set of labels of the Pauli operators of set E to ZD satisfying these two conditions. These are just consistency conditions. The first one says identity has to be assigned to 1. So if you do a measurement of the identity, you can only get one possible outcome. And then the second one is consistency for products of commuting operators. If you do a measurement of two commuting operators, TA and TB, the value assigned to the product has to be equal to the product of the values assigned to TA and TB individually. And then points in the phase space are identified with these non-contextual value assignments on the Pauli operators, where for each point, for each non-contextual value assignment function lambda, you have a phase space point operator that looks like this. So just a sum over the Pauli operators weighted by non-contextual value assignment. Now these phase space point operators, they form a basis for the space of Hermitian operators. And so any state can be expanded in terms of these. Looks something like this. And this is how we define the odd-dimensional discrete Wigner function. It's just the coefficients in this expansion. And since these operators are Hermitian, these coefficients are always real. If you take a trace of this equation, on the left-hand side, you just get 1. On the right-hand side, you get a sum of the coefficients. And so the coefficients are sort of normalized. That's why we call it a quasi-probability representation. The reason we can't call it a normal probability distribution is sometimes, for some states, they have to go negative. They take negative values. They're not, you can't interpret them as normal probabilities in general. So here's an example of what that looks like for a couple of cases. All stabilizer states have a non-negative Wigner function, meaning they are represented just as a probability distribution over the phase point operators. But magic states in general will have negative values. So here's an example of a magic state for a single qutrit. There are 4 phase space points back here.
for which the Wigner function goes negative. And you can turn this into a theorem. This is called the discrete Hudson's theorem. It says that all stabilizer states have a non-negative Wigner function. In fact, the only pure states with non-negative Wigner function are the stabilizer states, but there are mixed states that aren't mixtures of stabilizer states, which also have non-negative Wigner function. Now, this describes states, but in order to talk about quantum computation, we also have to talk about the dynamics of quantum computation. So these are Clifford gates and Pauli measurements. And this phase space also has some nice properties that you need for simulation of quantum computation. So first, phase point operators map to other phase point operators under every Clifford gate. It's closed under, the set of these phase point operators is closed under conjugation by Clifford gates. So another way to say that is the Wigner function is Clifford-covariant. This is the covariance condition down here. We get something similar for Pauli measurements. In that case, rather than a deterministic update rule, we have a probabilistic update rule. So here, pi is a projector representing a Pauli measurement yielding some outcome. If you do a Pauli measurement on a phase point operator, you map to a probabilistic combination of these phase point operators. So you don't map to a single point, you map to some distribution over the phase space points. And because we have these two properties, this is all the dynamics that come up in quantum computation with magic states. This yields a classical simulation algorithm of quantum computation that applies whenever the Wigner function of the input state is non-negative. So in that case, it is just a probability distribution, meaning you can sample phase space points from it. And that's basically what you do. You start by finding the Wigner function of the input state. You sample phase space points according to this probability distribution, and then you propagate the phase space points through the circuit. And whenever you come to a Clifford gate, you have this deterministic update rule. So the phase space point just maps to another phase space point. Whenever you come to a Pauli measurement, you need two things. First, you need some way of getting a measurement outcome. And that's easy in this case because these operators are identified with these non-contextual value assignments. You just return the value specified by this function lambda. And you have a probabilistic update rule. So you sample from this distribution and you end up with a new phase point operators carry on. But like I said, this only applies when the Wigner function of the input state is non-negative. And this gives a characterization of which states might be useful for quantum computation with magic states, because importantly, both of these update rules can be computed efficiently on a classical computer. So meaning whenever the Wigner function of the input state is non-negative, all of this can be efficiently computed classically. And so you need negativity in the representation of the input state to get something useful out of this computation. When the Wigner function goes negative, another classical simulation algorithm can be used. But in this case, the number of samples you need scales with this quantity R, which is just a measure of the amount of negativity in the representation of the input state. And this is expected to scale exponentially in general if you have products of magic states. And so in this sense, negativity determines the cost of classical simulation. And Hackup can tell you all about this if you want to know more about that. So this is all great. I mean, it's a great result. It tells you which states might be useful and which states certainly are not useful. But it only applies, like I said, it only applies in a limited case when the local qudit dimension is odd. It doesn't work for even dimensional qudits. So next thing I was planning to talk about this part 2 is these no-go theorems for discrete Wigner functions. This is for the even dimensional case. So here are the main results. I'm not going to go through the proofs in detail. I'll just mention them here. The first two say that no Wigner function for even dimensional qudits is Clifford-covariant, and no Wigner function for even dimensional qudits preserves positivity under Pauli measurements. And these were exactly the two properties that we needed to get the classical simulation algorithm to get all of these results. Basically, these great results we have for odd dimensional qudits, they don't apply at all to even dimensional qudits. If I have time at the end, I'll come back to this and go through where these results come from in a bit more detail. There's all kinds of connections to cohomology and contextuality and other interesting things. But for now, I'll just carry on with the other results. There's also this no-go result, which says, in order to simulate the kind of contextuality that comes up in quantum computation, even dimensional qudits, you need something like n squared bits, and the normal discrete Wigner function, the size of the phase space is 4 to the n, so linear number of bits. So in order to come up with some generalized phase space that might be useful for classical simulation algorithm, you need a bigger phase space, and a normal Wigner function won't work. So this tells us sort of how we need to modify the standard definition of the Wigner function in order to get a useful classical simulation algorithm. And that's what I'm going to talk about now. So, some examples of new quasi-probability representations that don't fit the definitions of the standard Wigner function, but do give the simulation properties that we want. So first, we can sort of boil down exactly what properties do we need our Wigner function to satisfy, or our quasi-probability representation to satisfy, in order to be useful for simulating quantum computation. Because the standard definition of the Wigner function has all kinds of other assumptions that aren't necessarily relevant here. So this is basically where these quasi-probability representations come from. You start by defining some set of phase space point operators, called these A sub alpha, where alpha and V is just the index set. We want these operators to be Hermitian. This means that the quasi-probability distribution representing states is going to be real. We want the trace of the operators to be 1. That means the representation of the states is normalized. We need them to span this full space of Hermitian operators on the Hilbert space, so that any state has some representation of this form. And then last, in order to simulate quantum computation, we need the Wigner function, or this new quasi-probability representation, to be Clifford-covariant, and it needs to preserve positivity under all Pauli measurements. So given that we have some set of operators that satisfy all those constraints, this is what the representation of quantum computation looks like. So roughly the same as before. We have some set of operators that span the space of Hermitian operators. So any state can be represented like this, where these coefficients are real and they add up to 1. They map to deterministically to other phase space point operators under all Clifford gates. And we have some kind of probabilistic update rule for Pauli measurements, where here, this is a probability distribution over both updated phase space points and measurement outcomes. So you sample 2 things here. You sample the outcome of the measurement and the new phase space point. So this is a slightly more general probabilistic update rule. So here's a yep.
Sorry, can you just say again what a superscript S?
Sorry, yeah. Yeah, so here, pi sub AS. A is a label of a Pauli operator. S is the measurement outcome.
Oh,
So
sorry, that's the opposite way around. Okay.
yeah, so this is a projector representing Pauli measurement A giving outcome S. Yeah. Here's a simple example of one of these slightly generalized quasi-probability representations. Stabilizer quasi-mixtures. So the set of density matrices representing stabilizer states span the space of Hermitian operators. And so any state can be represented as a affine combination of projectors onto stabilizer states. And they also have these nice rules for Clifford gates and Pauli measurements. So any stabilizer state maps to another stabilizer state under a Clifford operation, almost by definition. And if you perform a Pauli measurement on a stabilizer state, you end up back inside the convex hull of stabilizer states. And this gives this positivity preservation under all Pauli measurements. You can do a little bit better than this. This is another idea that we had a couple of years ago. It's similar to the standard discrete Wigner function for odd-dimensional qudits. The problem there, the reason that can't be easily extended to even-dimensional qudits, is the phase space point operators were based on non-contextual value assignments on the set of Pauli operators. But in even dimensions, you have proofs of contextuality like the Perez-Mermin square, which say that those functions don't exist. So this is kind of the next best thing you can do, which is rather than look at non-contextual value assignments on the full set of Pauli operators, you can restrict to subsets. And this is what we do. We look at subsets of Pauli operators satisfying these 2 conditions. So first is just a closure property. We call it closure under inference. If 2 operators are in the set omega and they commute, then the product also has to be in the set, because if you can measure each of these, then you can always infer the value of the product. And then we enforce explicitly that the set is non-contextual, meaning there exists one of these non-contextual value assignment functions for the operators in that set. And then the phase point operators are defined same as before. They're just weighted sums over Pauli operators, except in this case, rather than summing over all Pauli operators, you only sum over the ones in the set omega, and still weighting by the non-contextual value assignment function. So in this case, we have two different parameters to determine a phase space point, the non-contextual value assignment and the set over which it's defined. And so we end up with a much bigger phase space. It does satisfy that memory lower bound that I mentioned earlier. But the representation of the states is the same. It's just you expand a state as a affine mixture of these phase point operators. But since these are overcomplete, this representation isn't unique anymore. So there could be many different ways of choosing this decomposition. But other than that, everything is the same. So you still get deterministic update rules for these things under Clifford gates and probabilistic update rules under Pauli measurements. And so you end up with a classical simulation algorithm that looks exactly the same as before. The only difference is this representation of the state isn't unique. So now, given that we're relaxing the assumptions that usually go into this discrete Wigner function, you can ask, obviously you get more than you would if you did enforce those constraints. Question is how much more? This is another quasi-probability representation that we came up with a couple of years ago. The definition of this one is a little bit different. So this one we start by defining a polytope that we call lambda. So this is a subset of the space Herms of 1 of H. This is trace 1 Hermitian operators on Hilbert space H. And the polytope is defined like this. So it's the subset of this space satisfying all of these inequalities. So you get one inequality for each stabilizer state. Just the trace inner product with each stabilizer state has to be non-negative. So this is something like enforcing that if you do Pauli measurements on your state, you had to get non-negative probabilities. If you do other measurements, then maybe you would get negative probabilities, but we don't really care about those because in our model, we're only talking about Clifford gates and Pauli measurements. So this is the definition of the polytope lambda. This has a number of properties that also make it useful for describing quantum computation with magic states. So first, it has a finite number of extreme points, vertices, and we're going to call these A sub alpha. It's the vertices of this polytope that we're going to now identify with the generalized space-based point operators. Also, the polytope maps back into itself under Clifford gates and Pauli measurements. The one thing setting it apart from the previous quasi-probability representations is that lambda contains all n-qudit quantum states. So this means that any quantum state can be represented as a probabilistic combination of the vertices. So this is new. This is different from the previous cases. So because the polytope has these properties, we get these properties of the representation of quantum computation. So same as before, we start by representing the state rho as a probabilistic mixture of the vertices of lambda, except here, these coefficients can always be chosen to be non-negative. And then the representation of dynamics is the same as before. Vertices map to other vertices under all Clifford gates, and vertices map to probabilistic combination of vertices under all Pauli measurements. So there's no negative probabilities required anywhere. This is the key thing that sets this model apart from the previous models. The one thing we're giving up here is we don't have guarantees that these update rules can be efficiently computed. I'll say more about efficiency later on. But it does yield a classical simulation algorithm for quantum computation. It looks roughly the same as before. You start by finding a decomposition of the input state of the quantum circuit in terms of the generalized phase point operators, and you sample phase point operators from that probability distribution, and then you just propagate the phase point operators through the circuit. And when you come to a Clifford gate, update is deterministic. When you come to a Pauli measurement, you have a probabilistic update rule where you sample both an outcome for the measurement as well as a new phase space point. And here's a simple geometric picture of what this looks like. So this is a cartoon representation of the odd dimensional Wigner function. You have some convex set of physical density operators shown in red. The pure states are going to be on the boundary of that set, and the mixed states will be inside. And then you have some polytope which intersects non-trivially with the set of mixed states. The physical states inside this polytope, which is just the convex hull of the phase point operators, those are the ones with non-negative Wigner function, non-negative representation. And the ones that are physical states, so still inside the red shape, but outside of the polytope, those ones require some negativity. In this new case, this lambda picture, we have the same convex set of mixed quantum states. Inscribed in that set is the stabilizer polytope. So that's represented by this diamond here. That's just the convex hull of stabilizer states. Lambda is the dual of that polytope, the polar dual of that polytope. And so that's the square that I've drawn here. So it's got one facet for each pure stabilizer state. And the vertices of this shape are the ones that we identify with the generalized phase point operators in this model. And because every physical quantum state is inside the lambda polytope, this is why every quantum state is a non-negative representation in this model. This is part 4, so characterization of the vertices of lambda. First, why do we want to characterize the vertices of the polytope lambda? We have this definition of the polytope in terms of the half space inequalities. It's not so simple to turn that into a representation in terms of the vertices. So although the simulation algorithm applies to QCM, quantum computation with magic states, on any input state, the simulation is not efficient in general because we don't have this guarantee of efficiently computable update rules under Clifford, Gates, and Pauli measurements. But there are some special cases where simulation is efficient. So for example, in odd dimensional qudits, the standard phase point operators of the Wigner function, those are vertices of lambda. So if it were the case that you were starting with a state that were inside the convex hull of those phase point operators, then the simulation algorithm would be efficient. It's only when you go outside that set that you lose the guarantees of efficiency. So and you could have a bigger set of vertices for which you have efficiently computable update rules. And whenever the support of the probability distribution representing the input state is restricted to those vertices, the ones for which you have these efficient update rules, then the whole simulation algorithm will be efficient. And so this gives us a clear way of expanding the scope of what we can efficiently simulate on a classical computer just by characterizing more vertices and figuring out which ones have efficiently computable update rules. So that's the goal. But even still, even if we have a good understanding of the vertices, it's sort of hard to talk about scaling of quantum resources with the number of subsystems. And here's why. With the usual discrete Wigner function in odd dimensions, if you take a tensor product of 2 phase point operators, you get another phase point operator. And every phase point operator is constructed in this way as tensor products of phase point operators and fewer qubits, or fewer qudits. And this means that if you have a Wigner function of a product state, it just factors into a product of Wigner functions on 2 individual states. And so if you have multiple copies of a magic state, this quantity that determines the amount of negativity, it just scales exponentially with the number of subsystems. So talking about scaling is very easy in this picture. With the stabilizer quasi-mixtures example that I mentioned, it's a little bit harder because a tensor product of 2 stabilizer states is a stabilizer state, but there are other stabilizer states that don't factor in that way. And so rather than getting an equality here, we only get an upper bound on the negativity in the representation of this product state. But if you look at the 2 new models that I mentioned, so I'll go back. The one coming from the non-contextual sets of Pauli operators and the new one based on the lambda polytopes, phase point operators are not closed under tensor products. And so it's much harder to come up with statements like this about the scaling of resources. That said, you can say some things. So for example, a tensor product of 2 vertices is not a vertex of lambda. But you can do something like this, where you take a vertex and you tensor product with a density matrix or a projector onto a stabilizer state. That is still a vertex. You can also take a conjugate by a Clifford gate. That's also still a vertex. So tensoring on stabilizer states doesn't increase computational complexity of the simulation. But in general, talking about scaling of quantum resources is much harder. So here's another characterization of the vertices. So like I said, in odd dimensions, the standard discrete Wigner function phase point operators are vertices of lambda polytopes. For qubits, these phase point operators I mentioned before, as long as this set omega is inclusion maximal, then these are also vertices of the lambda polytopes in the qubit case. And these ones also have efficiently commutable update rules. And so for qubits, as long as your input state is inside the convex, all of these ones, you do have an efficiently you do have an efficient classical simulation algorithm. Now I'm going to spend some time talking about some new stuff. So I'll just go to the whiteboard. This is very new. We only finished the proof on Saturday, so I don't have any slides prepared yet, but I'll try to say something about it. So basically what we did is we found some new vertices of the lambda polytopes that we didn't know about before. So I'll just go through the definition. So first, you got to remember these ones. So an example of one of these vertices, we call CNC vertices, is where you take the set to be this one here. So x1, y1, z1x, zx, zy, and zz. And then phase one operator is just a sum over all of these with some signs up front. So a omega gamma looks like this. And so on. You just add up all of these operators with some signs. Now, you notice all of these operators pairwise anti-commute. Because of this, there's a connection to Majorana fermion operators. You can invert the Jordan-Wigner transformation to get a representation of these operators as Majorana fermion creation operators. This is something we want to explore more because in that picture, this just looks like a linear fermion Hamiltonian. So you can ask, what's the next most complicated thing? Like how can we generalize that? It turns out that all of these phase point operators, these CNC type phase point operators, have this structure. They're either a sum over Pauli operators that all pairwise anti-commute, or they're something like this, tensor product with a stabilizer state. Maybe mixed up with some Clifford operation. And so this is pretty general. So how can we generalize this? In the Jordan-Wigner transformation.
Sorry, could you just specify the level of generality? You're saying that even if you're like multi-qubit examples like this.
Yep. Yeah.
You now know that all of the extreme points are either of this Majorana form or.
Not all of the extreme points. All the extreme points that have integer coefficients. Those are the ones I'm talking about. So that's the ones like this with this non-contextual structure. All of these ones are either a sum of pairwise anti-commuting things or something like this with a tensor product of a stabilizer state. So we want to generalize this picture to get new vertices. That's what we're trying to do now. So the next thing we can do is rather than only look at linear fermion Hamiltonians, we can look at quadratic fermion Hamiltonians. So that's something we tried. So what that looks like is you can start by drawing the anti-commutativity graph. So these are the same ones as before. You write down the anti-commutativity graph of these operators. So basically everything pairwise anti-commutes, so it's just a complete graph. if you want to, and under the Jordan-Wigner transformation, these map to fermion operators. If you want to look at quadratic fermion Hamiltonians, you take products of these, right? And the graph theory picture, this just looks like taking a line graph. So for each edge here, you have an operator given by the product of these two operators, product of the ones on the vertices. So, for example, this edge would map to Z1. This edge maps to YZ. And whenever you have two edges that share a vertex, you have an edge between those two in the line graph picture. So for example, this one down here, product of these two is XX. This shares a vertex. This edge shares a vertex with this edge, but not this one. So you have a line here, but not there, and so on. You can expand this whole thing, and you end up with a big graph with 10 vertices. So what we want to do now is look at operators where the support is given by the vertex set of this graph. Okay, so if this graph is omega, this is the line graph of omega. We want to look at operators where the support is the vertex set of the line graph of omega. So these are defined roughly the same as before. A sum over Pauli operators, except we're using the ones in this set now, not in this one, possibly with some coefficients down here. So what we're doing is really restricting the support to operators that can be mapped to products of fermion creation operators. We want to make sure we're still in lambda, inside the lambda polytopes. And so we need to be careful about how we choose these coefficients. For example, if we choose them all to be plus or minus 1, we certainly end up outside lambda polytopes. And so we don't get the necessary properties for simulation and quantum computation. So basically what we do is we project the lambda polytope onto the space of operators spanned by operators of this form. So the ones where all of the other Paulis have 0 coefficient. And then we find the extreme points of that projected polytope. And if we do the projection carefully, if we choose a good projection, which in this case amounts to choosing these graphs, then the vertices of that projected polytope should map to vertices of the lambda polytope. So that was the hope. And it turns out, in some cases, that is true. So, for example, there are other ways of you could start with some other graph, take a line graph, and do everything the same way. But it turns out if you take a line graph of a complete graph, the extreme points that you get are vertices of the lambda polytope, and they look something like this. So this part's the same. Every coefficient is 1 over n, possibly with some sign. So this is a new infinite family of vertices that we didn't know about before. They sort of come with efficiently commutable update rules for free. And this already expands the scope of what we can simulate efficiently beyond normal Gottesman-Nil theorem, beyond CNC operators, and beyond all the previous quasi-probability representations. I'm going to go back to the slides now. Yeah, so we have these new vertices. Last thing I want to talk about is the size of the reachable phase space. So the reason for mentioning this is that the charge has been levied that the number of vertices of the lambda polytope seems pretty big. So it could be you're kind of hiding the complexity of simulation in the size of the generalized phase space. Right? That can't be said of the case of stabilizer states or Wigner function, because the number of phase point operator scales polynomially with number of qubits. In our case, we don't really know how many vertices there are. It's hard to figure that out. All we can do is numerics for some simple examples. So for example, for 1 qubit, lambda polytope is pretty simple. It's just a cube. It's got 8 vertices. Even for 2 qubits, numerics is a bit tricky. So we're in a 15-dimensional space. Lambda polytope is 60 facets, 1 for each stabilizer state, and it's got over 22,000 vertices, which fall into 8 orbits under the action of the Clifford group. And even for 3 qubits, we're in a 63-dimensional space. We can't even do numerics here. We don't actually know how many vertices the lambda polytope has. So it seems like the number of vertices, number of generalized phase space points, seems to grow very quickly with the number of qubits. But this isn't really a problem for us, because the thing we really care about is what happens if we start from a fixed magic state, right? So in this model, we almost always start with, a product of T states or a product of some fixed magic state. And if we start from a fixed magic state, then we can bound the number of phase space points, the number of vertices of the polytope that you can reach starting from that point. So you got a theorem based on this. Supposing you start, you could use a different state, but supposing you start from product of NT states, the number of vertices of lambda that you can reach by applying a circuit consisting of n pairwise commuting Pauli measurements can be specified with O of n squared bits. And it turns out, I don't know if this is well known, I think it is, but this isn't actually a restriction to a sequence of n pairwise commuting Pauli operators. This is universal for quantum computation. So although the total size of the phase space, the total number of vertices might grow very quickly with the number of qubits, the number of phase space points that you can actually reach is pretty small. So I'll just go through the proof of that. So remember, this is how everything is represented in this model. A state is represented as a probabilistic mixture of vertices, and then you have these two, a deterministic update rule for Clifford gates and a probabilistic update rule for Pauli measurements. There's this theorem called Karateodori's theorem, which says it's not about quantum computation. It's a general theorem in convex geometry. It says if a point in some d-dimensional space lies inside the convex hull of a set of points V, then X can be written as a convex combination of at most d plus 1 points in V. So, if you're representing a state, you don't need all the phase point operators. You only need some fairly small number of them. So, for example, for a system of qubits, we're in a 4 to the n dimensional space of Hermitian operators. We can choose the representation of the input state such that the support has size no more than 4 to the n. And we can do the same thing for the updates under Pauli measurements. We can choose the probability distributions so that the support is size no more than 2 times 4 to the n. In this case, the 2 is because there's 2 possible measurement outcomes. So supposing we do this, we can count how many phase point operators we can reach. So once again, we're looking at a circuit consisting of n pairwise commuting measurements. We'll label them A1, A2 onward. And supposing we do them on some initial state rho, and they give measurement outcomes S1, S2, and so on. This is what it looks like in the circuit description. You just do the measurements on the state, and you get the measurements. You end up with just a sequence of measurements. In the probability representation, so in this lambda hidden variable model representation, you're starting with a probability distribution over the vertices of lambda. And then every measurement is represented as another probability distribution. If you look at a single run, single sampling history of this simulation algorithm, at each step, you sample from some distribution. So first you're sampling from the initial distribution, and then you're applying measurements. You're sampling from these new distributions. Since the support of the input distribution had size no more than 4 to the n, you only need 2n bits to specify this, the first sample. And then you can do the same thing for every other sample. So to specify the first measurement, you need another 2n bits. To specify this sample, you need 2n plus 1 bits. And you can carry on this process. At the end of it, you're just adding up a number of linear terms in n. And so you need no more than quadratic number of bits to specify a whole run of the simulation algorithm. And because of this, you can only reach a quadratic number of vertices of lambda. Okay, and I think I have a bit more time. That's all I had to say about the quasi-probability representations. And so I'll go back and talk about the other thing I was going to talk about, which was these no-go theorems for discrete Wigner functions. So, this is the motivation for all of this. We had these results for odd-dimensional qudits, but they didn't work for even-dimensional qudits. This is why I'm going to talk about why they don't work for even-dimensional qudits. So first, this is the kinds of Wigner functions that we're going to be looking at. So Wigner functions constructed from operator bases. So they satisfy these 5 assumptions. First one is the operator basis assumption. So the phase point operators form an operator basis for the space of Hermitian operators. Then we assume that the Wigner function is real, which is equivalent to assuming the phase point operators are Hermitian. We assume it's standardized. So the phase point operators have trace 1. And then we have 2 more technical constraints, Pauli covariance constraint and a traciality constraint. So these 5 conditions define what we mean by a Wigner function. And now we want to say, when can a Wigner function satisfying these assumptions be Clifford-covariant, and when can it preserve positivity under Pauli measurements? Because those were the 2 properties that we needed for classical simulation. So like I said, in order for a Wigner function to be useful for simulating quantum computation, it needs to be covariant with respect to the Wigner function, where this is the Clifford covariance constraint. And it needs to have a positive representation for Pauli measurements. So that entails 2 things. You need some way of getting probabilities for measurement outcomes probabilistically. And you also need a probabilistic update rule once you apply the measurement. So if you do, Pauli measurement pi on state rho, if the original state had a non-negative Wigner function, then the resulting state also has to have a non-negative Wigner function. The source of why you can't do this for even-dimensional qudits has this cohomological underpinning. So this is what the cohomology looks like. You start by defining this chain complex, C star, where C0 is just ZD, and then C1 is the free ZD module over elements of ZD, over labels of the Pauli operators. And then second level C2 is free ZD module over commuting pairs. C3 is over pairwise commuting triples, and so on. And it's got a boundary map that looks like this. So for example, a face is represented by these 3 operators, and this is what the boundary looks like. Now, there's also a corresponding cochain complex, C star with a raised index, whose K cochains are given by ZD module maps from chains to ZD. And it's got a co-boundary map induced by the boundary map of the original chain complex. We can define this function beta, which is a 2 cochain. So it's defined like this, but by this relation here. So whenever you have 2 Pauli operators which commute, the result is going to be proportional to, TA times TB is going to be proportional to TA plus B up to some phase. So we define this function beta, which just keeps track of the extra phases that you pick up. So by definition, this is a 2 cochain. We can look at what happens to this function when we change the phase convention, right? Because in order to do any of this, we started by fixing a phase convention for the Pauli operators. So supposing we want to change this phase convention to go from, add some 0 cochain, go from gamma to gamma plus nu. The resulting change in beta looks like this. So beta goes to beta of AB plus nu of A plus nu of B minus nu of AB. This is just the addition of a co-boundary. Why do I mention this? We want to look at properties of Pauli operators, of Wigner functions, of all these things that are invariant with respect to this choice of phase convention. And so, we don't care about a fixed concrete form of this function beta. We care about equivalence up to changing this phase convention. And so the thing to look at is going to be beta up to addition of co-boundaries, which is exactly this cohomology class. So this is why we talk about cohomology in this picture, is because we want to look at properties up to changes of phase convention. So by definition, beta is a two cochain. It turns out it's a 2 cocycle as well. And this just comes from associativity of operator composition. So you can expand this relation in 2 different ways, so A and B first or B and C first, and you get this constraint on beta. And this is equivalent to just the co-boundary of beta being 0 on any volume. This means that beta is actually 2 cocycle. And the existence of parity-based proofs of contextuality actually hinge on whether or not this function beta is 0. So we have this theorem. If the qudit dimension is odd, then for any number of qudits, the phases of the Pauli operators can be chosen so that beta is identically 0, or equivalently, the cohomology class of beta is trivial. And proof is constructive. You just choose this phase convention, and it's always true. But this doesn't work for qubits. This was known already. For qubits, you have the Perez-Mermin square, which says you can't always, you can't choose the phases so that beta is identically 0. This is actually true for any even dimensions. So previously it was known for qubits. It's true for any even dimension, and proof is by defining a generalized version of the Perez-Mermin square. So if you have qudits of any even dimension, you define something like a local x operator and a y operator, and then the rest of the proof is identical. It just shows that the cohomology class of beta is non-trivial, and so you can't choose the phases so that beta is identically 0. And this is exactly what tells you whether or not there exists a Wigner function that represents Pauli measurements positively. So for any number of qudits of any dimension d, a Wigner function satisfying those 5 properties, there exists a Wigner function that positively represents Pauli measurements if and only if cohomology class of beta is trivial. And so for odd dimensions, it is trivial. And so such a Wigner function does exist. This is the standard odd dimensional Wigner function. For even dimensions, it's non-trivial, and so such a thing does not exist. So that this shows that the problem with constructing the even dimensional Wigner function is that it's because this cohomology class is non-trivial, which is equivalent to just there exist these state-independent proofs of contextuality. I think I'm going to skip over this last part, but basically you can do something similar for action of the Clifford group. It tells you when there exists a Wigner function, which is Clifford-covariant. So you start by defining this function, which keeps track of the extra phases that get picked up when you apply a Clifford gate to a Pauli operator. This function also has a cohomological interpretation. And I'll skip through the theorem because I'm running out of time. For odd dimensions, the cohomology class of this function is 0. For even dimensions, it's not. And this is the thing that tells you when a Clifford-covariant Wigner function exists. When it's 0, such a thing exists. So in odd dimensions, it does exist. But when it's non-trivial, then the Clifford-covariant Wigner function does not exist. So this proves that there's no Clifford-covariant Wigner function for any even dimensional qudits. And I'm going to end there so that we have some extra time. I'll just finish by mentioning that these are the primary references for these for this talk. So first one is the no-go theorems from cohomology, and then the other 3 talk about these generalized quasi-probability representations. And I'll finish by saying this is joint work with Gian, Robert, Paulina, Arne Heimandahl in Germany, and Larry.
Do we have any questions?
So for the even case or the relative group,
Yep.
you get any cohomology class, like anything or yours do one?
I don't remember what we get. I'd have to ask Jihan. Maybe I can do that and get back to you. Yeah.
Another question?
So I suppose I have two questions. One I can at least express quickly, which is, what does it mean cohomology? Homology?
Well,
Like, what is the particular homological? I mean,
I say cohomology, and not homology, just because, well, we start by defining a chain complex, and then we define the cochain complex as the dual to that. Everything that appears is the things that matter are the beta function and the phi function. You can track these phases. These live in the dual picture, not the primal picture. That's why I'm talking about cohomology, not homology.
yeah, okay. I mean, so maybe I'll try another one, which is what
Okay.
I learned now that I know there's this one theory of topological structure, even Hilbert's, like, it seems. Does this mean something about quantum computing is different? If I could only access odd dimensional Hilbert spaces?
Physically, it means physically the most easy, the most obvious phenomenology that appears is in contextuality. So basically, what it's saying is there exist state-independent proofs of contextuality using just Pauli operators for even-dimensional qudits, but not for odd-dimensional qudits. And that means, when you go to state-dependent proofs of contextuality in odd dimensions, the existence of a state-dependent proof of contextuality is the same as just negativity of the Wigner function. If there's negativity, then there's proof. If you're non-negative, then there's no proof. In even dimensions, that correspondence is not so clear because, just the measurements give proofs of contextuality. It's not so clear how to make the relation between negativity and contextuality.
And if I was trying to make, a relationship between power of computers and contextuality.
Well, yeah. So
Am I thwarted by this, or am I program?
not necessarily. It's just not so obvious, right? In odd dimensions, everything is very simple. You have this three-way correspondence between contextuality, negativity, and non-negativity, non-contextuality, and efficient classical simulatability. They're all equivalent in odd dimensions. And even dimensions, you have state-independent proofs of contextuality, and so this means it's not obvious how to define a Wigner function, and correspondence is not so clear. But you can still come up with these other quasi-probability representations. This is why we define these other quasi-probability representations in the first place, to try to restore this connection to power of quantum computation.
This talk is somewhere along the lines that what is it that makes that then simulated classically? So before you were saying the original that you have this complexity where arising from the negativity.
Yep.
And then you were throwing things where it's positive. So where does the exponential complexity come in?
Yeah. So yeah, in the odd dimensional case, all of the update rules under Clifford-covariant Pauli measurements, those are efficiently computable. And so the only source of complexity is in sampling of the initial state, and the negativity and the input state. When you go to these new representations, we don't have the efficiently computable update rules for Pauli measurements. So, sorry? Okay, yeah. Yeah, so we don't really know exactly where the complexity comes from, but there are now multiple sources. So it's not simply the negativity in the representation of the input state, because every state has a non-negative input, but that doesn't mean we can simulate everything efficiently. There is complexity coming from some other source.
You have a question? So you find all of this simulation with respect to Clifford update rules. But say in some abstract picture, could you change this to a different complete basis and some different set of operations that's sort of covariant with respect to that, rather than doing it with respect to Pauli methods?
I suppose you could. I don't see why not. It's not something I've thought about. Yeah.
It seems like you generalize one side of the story super general, but the other side left is.
You mean going from stabilizer states to arbitrary states is general? Yeah, we look at this picture because it has quantum computational universality. It is enough. That's why we started here. Maybe you could look at other models of quantum computation and get something else. I'm not sure.
And can I also just ask about the pre-fermion or the fermion mapping thing? I
Yep.
didn't quite catch it. What was the outcome of that? Like you find a bunch of those kind of taking fermions and doing joins with them.
Yeah, it's a new way of constructing vertices of lambda that we didn't know about before. And these new vertices come with efficiently computable update rules, and so they expand the scope of what we can efficiently simulate classically.
And is it just related to algebraic structures, or is it because it's something like it's related to like pre-fermions being?
That's something we don't really know. That's something we want to figure out. But like I said, we only finished the proof that these are vertices on Saturday. We don't know all that much about the connection yet. So we know they're useful for simulating quantum computation in this model. We don't really know much about the connection to the fermion description. Because in the first place, the fermion description was just useful for defining the operators. We don't really know if it gives us anything else.
You just said it's the algebraic property.
Yeah, exactly. Yeah.
So you get a discrete number.
Yeah. So I think Larry thinks that the connection is a lot deeper than that. He thinks there's something there, but we haven't figured it out yet.